For point 3.2, Compton scattering. Let's consider X-ray scattering next. Not only are X-rays scattered into various angles in a particle-like manner, the particle itself appears to change in that the X-ray wavelength shifts according to the angle of scattering. Compton will consider photons in a particle wave formalism by using the formula of Einstein's photovoltaic effect. Compton will also consider the photons in a relativistic setting, such that the special relativity energy momentum is the representation of the total energy. The scattering experiment will consist of an incoming, collimated X-ray beam striking a fixed electron with scattering of X-ray and recoil of He electron. Thus we have from conservation on energy relativistic. See equation 4-27, where F is the frequency of the incoming X-ray using Einstein relation with Planck's constant h, m is the rest mass of the electron, c is the speed of light, mc squared is thus the rest energy of the electron according to Einstein's special relativity. On the RHS we have the new X-ray frequency F', the non-zero electron recoil momentum p, such that the recoil electron's relativistic energy momentum is the square root of pc squared plus mc squared squared. For conservation of 4 momentum we have
see equation 4-28, which can be rewritten as see equation 4-29. And when combined with the conservation of energy relation we get the famous Compton equation. See equation 4-30. The angular distribution on the scattered photons is described by the Klein-Nishina formula.
See equation 4-31. Exercise. Derive the Klein-Nishina formula. 4.3.3. Theoretical discussion and examples. Thus far the scattering descriptions have involved potentials with attractive forces, like gravity or Coulomb with opposite charges. They could also involve repulsive forces with much the same result, as long as inherently coulombic, thus spherically symmetric, among other things. With the analysis as before, a variety of more complex potentials could be considered, but the essential quality is that there are asymptotic states and there are, maybe, bound states. We can largely determine the potential from ingoing asymptotic states that become scattered into outgoing asymptotic states by the non-zero interaction potential, or in turn verify our theoretical prediction for what that potential would be. This is where the rubber meets the road with theoretical physics connecting to experimental physics.
Note, when speaking of unbound asymptotic states, or free states, and bound states, we are speaking of two dynamical outcomes existing within the same dynamical system. We have seen this before, in the context of two-timing analysis and for perturbative analysis in general. Perturbative analysis assumes the dynamics of a reference system, then considers a second system, the perturbed system. We can see the asymptotic states that are free from the interaction of interest asymptotically by capturing them in our detection apparatus. The same can't be said for the bound states that we identify indirectly. Let's recap the key questions, according to Reed and Simon, that scattering theory seek to answer. See for further details. To get started, let's adopt their notation for free and bound states. Rho sub plus is asymptotically free in the future, T vector infinity. Rho sub minus is asymptotically free in the past, T vector negative infinity. And rho is a bound state. From the Hamiltonian formulation we know we can speak of a time transformation operator, acting on the aforementioned states with respect to a choice of Hamiltonian, here with slash without interaction, T sub t raised to the 0 power. Thus, it is possible to consider the asymptotic limits.
See equation 4-32. These limits are only well defined if solutions occur for pairs rho sub minus rho, where for each rho there is only one corresponding rho sub minus. Likewise for rho sub plus rho. The key questions. 1. What are the free states? Can they all be prepared experimentally? Completeness on preparation? 2. Is there uniqueness on correspondence rho sub minus rho and rho sub plus rho? 3. Is there weak completeness on scattering? E.g., map all rho sub minus onto rho is a member of normal sigma. Call that subset of normal sigma sub in. Repeat for rho sub plus to get normal sigma naught ut. Does normal sigma sub in equals normal sigma naught ut? This is known as weak asymptotic completeness.
4. Given the above, we can define a bijection of normal sigma onto itself, such that the following become well defined. Rho sub minus equals normal omega raised to the minus power rho, and rho sub plus equals normal omega raised to the plus power rho, where normal omega raised to the minus power and normal omega raised to the plus power are the bijective mappings. We can, thus, describe scattering in terms of a bijection. See the next equation. In classical mechanics, this will always exist as a bijection on the phase space. In quantum mechanics, S will be a linear unitary transformation known as the S matrix. 5. Are there symmetries? Sometimes S can be determined due to symmetries. This will be explored further in the QM context in 6. What is the analytic continuation? A common refinement for a real theory, to encompass wave phenomena, such as in transitioning to a quantum theory, is to shift to a complex theory by seeing the real theory as the boundary value of an analytic function. Analyticity of the S transformation, according to choice, also imparts causality, as with the Feynman choice of Cantor-integral definitions for propagators in
7. Is it asymptotically complete? Normal sigma sub BOUND plus normal sigma sub IN equals normal sigma sub BOUND plus normal sigma not UT? For classical mechanics, the plus operations are set theoretic, so this reduces to the question of whether normal sigma sub IN equals normal sigma not UT weak asymptotic completeness. Aside from a possible set of measure zero, i.e., there are set of measure zero issues. The set of bound states may be of measure zero with respect to the superset. In quantum theory, the plus is a direct sum of Hilbert spaces, which is more complicated and not discussed here. Example 4.1. Classical decay. Consider a classical decay, A3b, in which the first particle decays to 3 identical particles of mass m. Suppose that each final particle has the same energy in the CM frame, that the original particle moves with speed v along the lab z-axis, and that the decay energy is epsilon. If one of the particles emerges along the positive z-axis, at what angle to the z-axis do the other 2 particles emerge? Solution. We have the same energy in CM frame, i.e. same momentum. Thus, in CM frame, 1/2 times 3m times v squared equals 3, and 1/2 times m times v prime squared plus epsilon, mv prime, equals the square root of m squared v squared minus 2/3 m epsilon, and
see the equation shown. Thus, see the next equation. Exercise 4.1. Classical decay. Example 4.2. FNW 1.14. Consider Rutherford scattering off of a nuclear surface when the cross-section to strike the nuclear surface is sigma sub r equals pi b squared for impact parameter at minimum r sub min equals b. Recall that the system energy asymptotically, with ingoing velocity v sub infinity, is simply. See the equation shown. We also have 4, conserved, angular momentum.
See the next equation. Thus, the effective potential with indicated m sub theta and Coulomb potential v sub c equals zze squared over r is. See the equation shown. Thus, see the next equation. Related exercises. See Fetter and Waleka.
Example 4.3. FNW 1.17. Consider scattering off of the potential. See the equation shown. 1. Show orbit is identical to a light ray refracted by a sphere of radius a and equals the square root of e plus v sub 0 divided by e. 2. Find the differential elastic cross-section. Solution. 1. Recall f of 2 pi b dB equals f of d sigma sub d of theta and times d normal omega equals 2 pi the sine of theta d theta right double arrow d sigma over d normal omega equals b over sine theta times the absolute value of dB over d theta. Have mv sub 1 the sine of theta sub 1 equals mv sub 2 the sine of theta sub 2 and e equals the fraction with numerator p sub 1 squared and denominator 2m plus u sub 1 equals the fraction with numerator p sub 2 squared and denominator 2m plus u sub 2. Thus,
see the next equation. Thus, the orbit is identical to a light ray refracted by a sphere of radius a and north equals the square root of e plus v sub 0 divided by e. See the equation shown. Deflection angle corresponding to theta sub 1 and theta sub 2 is theta equals theta sub 1 minus theta sub 2. Thus, theta sub 1 equals theta over 2 plus theta sub 2, and since B equals the sine of theta sub 1 we have.
The sine of theta sub 1 equals the sine of open brace theta over 2 plus theta sub 2 close brace equals the sine of theta over 2, the sine of theta sub 2 plus the cosine of theta over 2, the cosine of theta sub 2 equals the sine of theta over 2, the sine of theta sub 1 over n plus the cosine of theta over 2, the square root of 1 minus the sine squared of theta sub 1 squared. See the next equation. B squared equals a squared the sine squared of theta sub 1 equals the fraction with numerator a squared n squared the sine squared of theta over 2, and denominator positive n squared the sine squared of theta over 2, plus 1 minus 2 n the cosine of theta over 2, plus n squared the cosine squared of theta over 2, equals the fraction with numerator a squared n squared the sine squared of theta over 2, and denominator 1 plus n squared minus 2 and the cosine of theta over 2.
See the equation shown. Equals the fraction with numerator a squared n squared and denominator 1 plus n squared minus 2n the cosine of theta over 2. Squared times open brace the sine of theta over 2. The cosine of theta over 2 times 1 plus n squared minus 2n the cosine of theta over 2 minus n the sine cubed of theta over 2 close brace. Thus, see the next equation. Related exercises. See Fetter and Waleka.
Example 4.4. FNW 1.18. Consider a small particle at large impact parameter B from central potential V, R, with only a slight deflection occurring upon scattering. A. Use an impulse approximation to derive the small deflection angle. B. Examine the case V of R equals gamma R raised to the negative n power, where both gamma and n are positive. C. Examine the case V of R equals gamma E raised to the negative lambda R power. D. In QM the small angle part of the cross-section is different than classical. Discuss. Solution. A. In the impulse approximation we have theta sub 1 almost equals the fraction with numerator p sub 1 y prime and denominator m sub 1 v sub infinity, and p sub 1 y prime equals the integral from negative infinity to infinity of f sub y of dt equals the integral from negative infinity to infinity of negative du over dr times y over r dt. Assume small deflection y equals b dt equals the fraction with numerator dx and denominator v sub infinity. See the equation shown. B. V of r equals gamma r raised to the negative n power times r is greater than 0 and is greater than 0.
See the next equation. Thus, theta equals the fraction with numerator c and denominator b to the nth power times c equals 2 over mv sub infinity squared the integral from 1 to infinity of the fraction with numerator x raised to the negative n plus 1 power and denominator the square root of x squared minus 1 dx. So, see the equation shown. Thus,
see the next equation. For n equals 1 d sigma over d normal omega asymptotically equals c prime theta to the negative 4 power Rutherford, d sigma over d normal omega, sub el equals c z cubed over 4e sine squared 1 half theta, squared. N equals 2 d sigma over d normal omega asymptotically equals c prime theta to the negative 3 power, d sigma over d normal omega. Sub el equals gamma pi squared over e sine theta times the fraction with numerator pi minus theta and denominator theta squared times 2 pi minus theta squared. For sigma sub tau to be well defined, the integral from 2 of d sigma over d normal omega is less than infinity. Here we have. See the equation shown. So, the cross-section is only well defined if n less than 0.
C have V of r equals gamma e raised to the negative lambda r power times r equals bx. See the next equation. Consider b lambda is much greater than 1 only x almost equals 1 contributes. See the equation shown. Thus, theta equals gamma the square root of pi b over lambda the negative lambda bth power of e of lambda over m sub 1 v sub infinity squared. Since, see the next equation.
Thus, sigma sub tau not well defined because the integral from 0 to x of the fraction with numerator dx and denominator x log x equals the log of log x sub x vector infinity raised to the power vector infinity. D. Classically, no zero-angle scattering for finite b, while QM has finite probability density for zero-angle scattering. Related exercises, see Feder and Waleka.